Hi, today I want to start to teaching isomer and isomerism. The first step is the definition of the isomer. What is the isomer? Isomer, the compounds have the same molecular formula but different structure. In this situation, we have to classify isomerism first. We have two main groups for the isomerism: structural, or we can say constitutional isomer, structural or constitutional isomer, and the second one, stereoisomer. Okay? A structural isomer has a different structure, but in the stereoisomer, the different structure in the 3D form, in the space, but the formula is the same. In the structural isomer, we can divide for the three groups. Regioisomer. Okay, as you see in the regioisomer, the position of the functional group or compound is different. For example, I have this compound, 2-chloro butane, and I have other compound, 1-chlorobutane. They are regioisomer because the position of the chloride is different in these two compounds. Second one, bounding isomer or binding isomer. Okay, different type of the bound. For example, I give an example. Diethyl ether. Okay, the same structure with the butanol. One butanol and diethyl ether has a different bound. Or I can say, other example, cyclobutane, and 1-butane. As you see, they have a different bond, and same chemical formula. And the third one, tautomerization. Tautomerization, when the position of the double bond and the hydrogen, usually in the alpha hydrogen, change. For example, I have this example. It is a anode. If I change the double bond here, okay, to oxygen, come here. As you see here, this hydrogen will go here, and this double bond comes here. For better understanding, I draw the open form, CH3, CH, double bond, CH, OH. Okay, usually the oxo form is the more stable. I put hydrogen in this position, okay, and I bring double hydrogen. Hydrogen is here. CH3, CH2, CH is here. As you see here, I put hydrogen in this carbon, and I bring double bond for between the carbon and oxygen. Mainly, this is the tautomerization. Hi. A stereoisomer can be divided in two groups, configuration and conformation. Okay, and as you see, configuration and conformation. And the configuration can be divided into two groups, geometrical and optical. Optical. Okay. In the geometrical, we can classify for two types of the compound, usually cycloalkane and alkene. And optical isomer can be divided two groups, absolute configuration and relative configuration. Okay, absolute configuration we will study in the optical isomer, can be in two types, R and S, and the relative configuration can be two types, D and L. And this is very easy. Conformation also we can study in the alkanes. Okay, and in the cycloalkanes and cycloalkanes. We continue with the conformation of the alkane. As you know, conformation of isomer is a spatial arrangement of the different atoms or functional groups. I start with two examples and I explain the energy level in the alkane in different conformation and what situation we can see in this part. For example, the first example is the ethane. Ethane in this structure, CH3, CH3, okay? And as we see in the Newman projection I showed before, we can see in this carbon, if I look from this side, in the middle, and the hydrogen is in that part. Okay? And this hydrogen is exactly behind that hydrogen. Okay? If I rotate 60 degrees this bond, okay? I draw the energy diagram, 0, 60, 120, 180, 240, 300, 360. As we see here, this shape is eclipsed. Higher energy, more repulsion, higher repulsion. I can choose from here, I can say, this is in the 0 degree, what I have. If I rotate 60 degrees, the sigma bond, the shape will be in this position. And it is a staggered. Hydrogen is more distant and less energy and less repulsion. and I can show less energy, for example, in the 60, I choose this one. If I again rotate 60 degrees, fortunately, I will have the same shape. Because it is exactly the same, I can make a line like this one. Okay, in the 120 again. And if I rotate one more, it will be again staggered in 180, and 240, 30, and 360. The shape will be like a okay. This line will be eclipsed. This line will be staggered. The other example is the butane. When we try to see from the carbon 2 to 3, carbon 2 to carbon 3. In this situation, if I want to draw the Newman projection of this compound, I see this carbon in the middle. I have one methyl for binding to it, 2 hydrogen. It is the carbon 3, which bind to one methyl, and the 4 also 2 hydrogen, 4 bind. As you see here, 2 methyl groups behind each other and close to each other, higher repulsion, and it is a thin periplanar. Okay, I drew the energy diagram. 0, 60, 120, 180, 300, and 360. Okay, I rotate this bond 60 degrees. Okay. The first part is the same, but carbon number 3 rotate, and the metal groups will be a little far with 60 degrees. And we call this compound, this shape, gauche. Or we can say thin clina. As you see, the energy is lower than this one. I choose the highest level, high level energy. Start from the first compound, and the second compound, because it is eclipsed, it is a staggered, less repulsion. I choose for 60 this point. It is a gauche. And if I rotate again 60 degrees, this metal comes for here, this hydrogen go here, and this hydrogen go here. And in this situation, behind the methyl I will have a hydrogen, but behind hydrogen I will have a methyl. Compared to the first eclipse, the second eclipse has a less repulsion because the 2 methyls just closer to 2 hydrogen. And we call this shape is anticlinal. Anticlinal. As you compare to the energy, this energy is the higher than the gauche, but less than simple planar. And then I can choose the less than. If I choose this line, the highest energy, I can choose between these two will be like this. Again, I rotate 60 degrees. Metal, this hydrogen comes here. This metal comes here. Now the metals is the far from each other, and the less the repulsion, lowest repulsion we can see here. When we say anti-periplanar, it's called anti-periplanar, and the energy must be lowest. Okay, it is a staggered again. It is of course a staggered, but it is the lowest energy because it has stability. And in this situation, 180 must be closer than this, and I can show the lowest energy. Then, if I draw the energy level here, this decrease, increase, and decrease again. If I can rotate 60 degrees, this metal will go here. Okay, this hydrogen go here. Okay, this metal go here. This hydrogen go here. As you see, this shape exactly the shape of the anticlinal. Then we can say the same. They are the same. And then I can show this is the anticlinal here, and in the 120, 140, 240, I also have to choose anticlinal. Okay, and the energy comes out until this place. If I rotate again 60 degrees, this metal go here. Okay, this metal closer, and it will be harsh H and H. It will be exactly the same of the gauche or synclinal, and in this situation I can show exactly the same situation of the synclinal. Okay, I can draw until here. Okay, and the last degree, 60 degrees, this metal again will be closer to the metal, and the hydrogens will be closer to hydrogen. And it is a eclipsed again and simple planet. It is the highest energy level in this situation. As you see in this structure, very easy, very nicely, we can manage it. It is a simple planet. This is a simple planet. Both of the metrics has the highest energy. This two is the gauche or synclinal. Okay, I can show from here. It is also synclinal. It is anticlinal, and because of both of them has the same situation. Sorry for this one. Okay, and it is both of them is anticlinal, and the last one is antiperiplanar with the highest stability. High stability. Now we study about conformation of the cycloalkane. We start from the smallest cycloalkane, which is the cyclopropane. Okay, as in a cyclopropane, the carbons are sp3. Okay, we studied in the last lecture from the root sp3 must has tetrahedral shape, geometrical shape, and 109.5 angle. But if I draw the cyclopropane here, it will be like this shape. Okay, as you see here, hydrogens, hydrogens. Okay, and I have a 2 hydrogen here. Or I can draw like this. Okay. And this part will be closer. Okay. Okay. And see, it is a triangle. In the cyclopropane, the angle is at 60 degrees. Okay? And from the 109.5, 49.5 degrees is smaller. And it makes the higher repulsion and a big problem in this molecule, and it decreases stability. And we call it angle strain. Or we can say Baeyer strain. The name is the Baeyer strain. Okay? Because as usual, the species must has a 109.5 angle, but it is 60 and 49.5 is smaller. And as we see here, all of the hydrogens here is a highly reactive, okay, and all in the eclipse form. And we say torsional strain. And the other problem is the torsional strain. Because it is all of the hydrogen, because of the situation of the compound, okay, all are eclipsed and higher energy, and because of this, it has a torsional strain. It's a very unstable compound. For example, if I have a cyclopropane, if we react with the halogens, okay, as you know, we will study later, cycloalkane has a radical substitution with the halogens, but here can be ring opening happen. It's really easily can ring opening happen. Second compound is the cyclobutane. Cyclobutane for example, I drew like this shape. Okay? It is a little folded, and the shape in the geometrical, it will be like this. It is folded. You see, we can like draw like this one. And the angle around 88 degrees. And the hydrogen be again in this situation. As you see, the angle difference between the 109.5 and the 88 is a little lower. In this situation, we can say this compound higher stability compared to the cyclopropane, because cyclopropane has a 49.5 degrees smaller, but here we have (21.5). Again, it has angular strain and torsional strain. Angular strain and torsional strain. And it has a lower stability but higher stability compared to the cyclopropane. And the third one is the cyclopentane. Angle almost 105. As you see, very closer to the 109.5. And the less repulsion, less angular strain, and less torsional strain. Both of them have a less and higher stability. And because of this, we can see cyclopentane, usually in the organic chemistry. And the next group is the cyclohexane, which is the main part and very important. We will study in the next lecture. I hope this lecture was very good and have a good time.